So this talk will be devoted almost entirely to the problem of inverse iteration. I think in many ways the QR algorithm is perhaps the most beautiful thing in numerical linear algebra, or at least as far as dense matrices are concerned. I think inverse iteration, on the other hand, is perhaps the most interesting because the results associated with it are really rather surprising. The interesting thing is that from a strictly mathematical point of view, they are almost exactly the same, and that doesn't seem to be generally recognized, so I'll try to bring out the connection between them. Well, first of all, what is inverse iteration? Well, it's a fairly natural offshoot of the power method. In the power method, essentially, you start off like this. You take an arbitrary vector x0, and we'll assume for the moment we have a complete set of eigenvectors. You can express it in the form sigma alpha I vi. And now if you were to form successive powers of ax0, a squared x0, and so on by this sequence x, s plus 1 equals axs, then we will have that xs is sigma alpha I a to the s vi, which is sigma alpha I lambda to the s vi. So supposing the eigenvalues are ordered decreasing magnitudes, and let's assume for the moment that lambda 2 really is larger than all the others. The others may include some of equal modulus. But then we can write this in the form lambda 1 to the s alpha 1 v1 plus sigma from 2 to the n alpha I lambda I over lambda 1 to the s times vi. And lambda I over lambda 1 is 0, is less than 1 for each of the others, and so this thing is tending to 0, and therefore ultimately our vector is tending to a multiple of v1, the dominant eigenvector. Of course, if we were unfortunate in our choice of arbitrary vector x0, we may happen to choose one that had no component of v1, and if that happened, of course, we wouldn't in fact get converge to v1. In practice, of course, rounding errors will be made so that even if you were exactly deficient, it would probably creep in and ultimately converge to v1, but a rather poor choice would obviously lead to considerable inefficiency. The speed of convergence, of course, is determined by this rate lambda I over lambda 1 to the s. And therefore, if the second eigenvalue is fairly close to lambda 1, the convergence is going to be slow. And it's exactly the point that I was making in connection with the QR algorithm without shift. Well, I've described it directly in that form. Usually, in order to stop numbers getting either very large or very small, you have some normalization at each stage, and you have that xs plus 1 is equal to some multiple of axs, this multiple being chosen so that all vectors in the sequence are normalized. But that really doesn't affect it. The direction of each vector remains the same in this modified sequence. It's just numerical convenience. I don't know that I should use the term just numerical convenience, because really that's all we're talking about, I suppose, in these lectures. Well, clearly this has severe limitations. As I described it, you could only find the dominant eigenvalue, and that possibly rather slowly. And so again, you get the history of the power method. The whole history is attempts to overcome this weakness, to speed up the rate of convergence, and also to find some technique which would allow you to find the other eigenvalues and eigenvectors. And easily the most important, certainly as far as the handbook is concerned, that is with dense matrices, is inverse iteration. And that is based on the observation that if you take a minus ki to the minus 1, its eigenvalues are 1 over lambda I minus k. And the eigenvectors are the same as before. So that if you can choose k so that it's a good deal closer to lambda I than it is to any of the other eigenvalues, this now becomes the dominant eigenvalue of this matrix. And so if we do the power method using this matrix, then we will get convergence to the eigenvalue nearest to k. And inverse iteration is used in lots of different ways, sometimes with the k, which is, has been determined by a very good eigenvalue program, so that k is the sort of the best approximation we're capable of getting to lambda I. Sometimes it's done with a fairly good approximation, perhaps with 2 or 3 decimals right, and sometimes in a situation rather weaker than that, where you have some reason to hope that the k you've chosen is rather nearer to the eigenvalue you want than it is to any other, in which case one does. In the first case, lambda I minus k is so small, and therefore this reciprocal is so large, that convergence is fantastically fast, and I'm going to be talking about algorithms in which you expect convergence to take place in one iteration. Well, it has a long history, inverse iteration. It's often called Wieland iteration, and I think it's certainly true that the first mention of it in the literature comes in a paper by Wieland. It was certainly been discovered independently by lots of people. We used it at MPL. I think at MPL, both Fox and I used it independently. But I think the things that we all did way back in the early 40s are really not terribly relevant to the modern inverse iteration. I mean, a tremendous amount has happened since then, and we know a lot more about it and how to use it. I say you iterate with a minus ki to the minus 1, but of course the one thing you don't do is to form the inverse of this matrix. You now have a minus, I tend to prefer p in practice because I usually use k as my normalizing factors. Now I determine the next iteration from the previous one by solving this set of linear equations, usually with a normalizing factor in it. So that's the way in which it's done. Now, if you read any early references to the method, we hope to use this with a value of p, which is fairly close to an eigenvalue. And the closer it is to an eigenvalue, the faster it's going to converge. But we were all terribly worried about what happened as we got close to an eigenvalue, because p is getting singular, and the typical step in the algorithm then is to solve a very ill-conditioned, possibly singular to working actually, system of linear equations. And so you'll even see warnings in some of the early references. You can use this, but don't take a p that's too good, or your matrix will be nearly singular and your solutions will be bad, and that this will have a harmful effect. Well, that turns out, in fact, not to be true. And the one thing that really doesn't matter very much is the near singularity of this matrix. Indeed, you can go on using it right up to the point where p is so good that this is singular to working accuracy, or even in some cases exactly singular. Now, let's see, but first of all, let's look into that a little bit. In practice, how can we recognize whether we've done a reasonably good job in getting an eigenvalue, an eigenvector? Let's assume we've got a normalized vector x, and just for convenience, so that I don't have to keep normalizing everything to decide whether it's large or small, I'll assume that a is normalized so that its norm is roughly equal to unity. And x is a unit vector, possibly in the L2 norm, but certainly roughly of unit length. Well, if I really had got a pair, I would have that ax minus lambda x is equal to r, the residual. This residual would be 0, and if it's exactly 0, then it is an exact eigenvalue and eigenvector. But let us take that relation for the moment, whether r is small or not. We just define it by that equation, and we can write it in the form r minus r xh times x equals lambda x, because I've assumed that xhx is 1 because I've got a normalized vector. And so an interesting way of looking at that result is it says that lambda and x are an exact eigenvalue and eigenvector of this matrix here. So if my R is small, round about noise level, so if norm R is sort of the order of magnitude of 2 to the minus t times a, which in this case is just 2 to the minus t with just a smallish factor here. Perhaps if n were large, I would permit something around about order n or so. Then this would say that lambda and x were exact for a perturbation of a of the order of noise level, and this would really be the best I could expect an algorithm to achieve. It may or may not be a good eigenvalue. It would depend just how sensitive eigenvalues and eigenvectors were. If they are sensitive, then of course the implication of this result would be lower. But of course, we would expect to have a poorer result judged on absolute terms in the case of an unsymmetric A. Well, what's the relevance of this to this situation here? Let's, for the moment, remove the normalization and so that I'll get my new vector just by solving the equations, and I haven't yet. XS is normalized. A, I assume, was not normalized. P, I hope, is a very good approximation to an eigenvalue. Let's do a step of iteration. How will I recognize that I've been successful? And I say I will have been successful if the norm of ys plus 1 is large, and the larger it is, the more successful I've been. And the proof is really rather trivial. We get, from this relation, we get that. And now this is the normalized vector. And that's xs plus 1 is equal to x over ys plus 1. And therefore, if y was very much larger than the normalized x from which I started, this residual is very small. So if in particular I got enormous growth, if y grew up to the size of 2 to the t, that is the reciprocal of the rounding errors on the computer, then this would mean that the residual was down at noise level. And it would mean that P and xs plus 1 were exact for a matrix which differs from A only by noise level, and I'd be at the limit of the resolution that I could expect with the computation that I'm using. Well, you might say that's all very well, but if P is very near to an eigenvalue, and it's that I'm discussing at the moment, I'm hoping P is near to an eigenvalue, then I'm solving an almost singular system, and therefore the y I get in practice won't be anything like the y that I ought to have got. I'm solving a very unconditioned set of equations, and so the computed y will be very different from the true one. And at first sight that looks rather discouraging until you think back to what the error analysis says about it. And the error analysis says that A minus E minus PI times ys plus 1 is equal to xs. It says that the error analysis, just to make it so that I could make this claim without any exceptions, I would assume that I've solved this set of linear equations by the QR factorization. If I use the QR factorization, I can make this claim without any exceptions. If I use Gaussian elimination with pivoting, I have to say that this result is true provided there hasn't been any appreciable growth. In practice, I know there's usually not growth, so that in practice the statement that can be made about Gaussian elimination with pivoting is about as strong as the QR, but I don't want to be troubled with that at the moment. Well, now we have the same effect. If ys1 has grown, I have A plus E minus PI, ys plus 1 over ys plus 1, which is my new xs plus 1, is equal to xs over ys plus 1. And this means that A, and that's what I call R. So if I get the full growth, R will be at noise level, and I'll have A plus E plus R xs plus 1, sorry, minus R xs plus 1 H times xs plus 1 is equal to pxs plus 1. And again, I have that the p and xs plus 1 are exact for this perturbed matrix, and now I have two perturbations, but they're both at noise level. And so the actual errors made in the inverse iteration, although they have an enormous effect on ys plus 1, they don't harm the result I'm trying to get. Now, at first sight, that may seem rather odd, and perhaps we get some insight into it by considering the simplest case. In fact, the case that would always arise if we're thinking of it as a classical analyst, in which the nearness of p to lambda was as close as we pleased. Well, what would happen when we did the Gaussian elimination to solve this set of linear equations is we get our upper triangular matrix, and if the lambda were sufficiently close, this last element would be very, very small. And the right-hand side, after it was eliminated, would be ordinary size. And then you do your back substitution, you get a huge element here, which is what you hope you'll get, and all the other elements would be huge. Now, when you make a rounding error, what will happen in the well-conditioned case, instead of getting the epsilon you should have got, say we'll call that epsilon 1, the one you should have got, you'll get a different one, epsilon 2. It might even be the wrong sign. It might be about twice as big it should have been. Maybe it should be about 10 to the minus 10, you get 2 times 10 to the minus 10. But what will happen, if you consider the solution of this, you'll find that if the value you get is twice what it should be, the solution is almost exactly the same as before, except that it's twice as big. You find that really this bit is virtually ignored, and all the solution comes from this. You get a very large thing there, and then when you get the next component, it's just the ratio of that to that times this large thing plus this little bit here, and this doesn't make an effect. So that in the standard case, and in fact in pretty well all cases, if you could go on to the limit, you'd find what happened is that your vector, instead of being what it should be, will just be a multiple of what it should be, and we're not worried about multiples as far as eigenvectors are concerned, and therefore, sort of crudely, that's why it works. To see why it really works, though, this error analysis covers the situation and ensures that you're getting something close to A. Well, let me now establish in practice, you're still considering the possibility of, we still consider the possibility of doing a number of steps of iteration, though mostly in the handbook we're hoping to get away with just one iteration. But observe that we needn't use the same shift each time. We can change the shifter every time if there's any advantage in doing it. And just for the moment, I'll consider what happens if we are using, at step number S, we use a shift PS. And it turns out that inverse iteration with AT is the same as the QR algorithm with the matrix A itself. I say it's the same for the moment. Obviously it isn't the same. It's difficult to think of any two things that are much more different at the moment. We're going to show there's an extremely important relationship. So let's consider now inverse iteration defined by A minus PSI times XS plus 1 is equal to KS XS. So starting off, the first one being, yes. Do I want, yes, starting off with A minus P1I x1 equals k0 x0. It's always a difficult thing to know whether you should start off with x0 and x1 in order to establish the relationship more easily. Well, sorry, I'm going to do inverse iteration with AT. So that's the process I'm thinking of, and I will get that yes. I'll get that xs is pi ki pi at minus pi I to the minus 1 times x naught. So that's what happens if I do inverse iteration. That's how the s iterate depends on the first one. Now let's consider the QR algorithm performed with the same set of shifts. You remember that I proved that Q1 up to Qs times Rs down to R1 was equal to A1 to the S. That's the unshifted thing. Well, if you go through the analysis I used to prove that, you find the corresponding result for the shifted thing is that this is pi A1 minus, the shifts are now pi rather than ki. Sorry. You find that, which was, when the pi is a naught, it reduces to the result I proved. Proving that result is quite simple. Now I'm going to try and establish a relationship between these, and I find that writing this big QS, big RS equals pi A1 minus pi I to the minus 1. No minus 1 in it yet. So let's say this is RST, QST equals pi A1t minus P1i. And of course A1 is nothing other than A. There's no other thing but A in this. And I can write that as QS is equal to pi AT minus PII to the minus 1 times RST. Yes, just that. Now let's consider the fact when we start off with x naught equal to En. By definition, xs is a unit vector. Now what is this on the right-hand side of here? En times this matrix is just the last column of this matrix. So that xs is a unit vector in the direction of the last column of this product. Okay. Now let's look at this result here, and we get qs times En. Multiply this by En. We get that is equal to this same product, the same product that we've got there, times RST times En. Okay, what's RST by En? RST is a lower triangular matrix. When we multiply it by En, we take its last column, and so its last column of a triangular matrix. It's just something like that, and so it itself is a multiple of En, some other multiple of En. And what does this say? This says that the last column of QS is equal to, is parallel to the last column of this thing. And the last column of QS is a unit vector, so it's a unit vector in the direction of the last column of this product, which is precisely what xs is. And so you find that the last column of the big QS is, in fact, with exact computation, exactly the same as the xs obtained in s steps of the inverse iteration. And the last column of the QS obtained from the QR algorithm, perhaps I should say. The interesting thing is you can go further, and perhaps I'd better not do that because it's a good deal to do yet. You can show that I've established this relation assuming in some mysterious way we've done in one place the inverse iteration with a set of shifts, and somewhere else we've done the QR algorithm with the same set of shifts. That would be true whatever the shifts were, however they've been derived. But now I'm going to consider the particular case when the shifts I use are obtained by using the last element. In the QR algorithm, they're obtained from the last element of the current matrix. And I'm going to compare that with the case in which the shift is obtained from the Rayleigh quotient from the corresponding thing. Then I can prove that the two sets of shifts obtained in the two processes are the same, and we already still have this relation, which is true. And so you have this exact tie-up, in theory, between the QR algorithm and, of course, its rate of convergence and inverse iteration. I think it's very nice that this is true, and it goes a lot to explain. I think one's not surprised that inverse iteration has high speed of convergence. So it goes, well, it's very nice to tie them up and see two of the most powerful techniques, which numerically are very different. The way in which they're stable is entirely different, and of course, because of the feature I'm pointing about here, about the computed ones being so different, the tie-up between the numbers that arise in practice isn't like that at all. They have the same theoretical basis. Okay, well, now we come to a rather surprising situation. And some of the most interesting things connected with inverse iteration really arise from the mathematical theory. They don't arise from the numerical part of it. It's very easy to imagine that anything that happens in connection with inverse iteration that you don't understand comes because you're trying to solve an almost singular set of equations. So when it behaves in a bizarre fashion, you can say to yourself, well, that's what you'd expect if you muck around with almost singular matrices. And the interesting thing is that the phenomena I'm going to describe, strange though they are, have nothing to do with rounding errors, and so we can forget about rounding errors for the moment and consider what would happen if we did exact calculation. So now we're going to stick with a fixed p and have a process described like that, or to describe it without the normalization, and then do the normalization as a separate issue. It is ys plus 1 over norm ys plus 1. Now, if you go back to the initial motivation, we started off with the power method. We saw it didn't converge fast enough. We saw that we could get better speed of convergence by doing inverse iteration using values of p near to eigenvalues. This enabled us to get any eigenvector instead of just the dominant one. That was the whole motivation. And it was based on this thing in which we now had sigma alpha I times the eigenvalues of the matrix we're using, which I'll call mu sigma alpha j, mu j over mu I to the s times vj. Sorry, that's mu. Well, the mu's are now the 1 over lambda I minus p's. And we saw about when lambda was nearer to, when p was nearer to lambda I than any of the other eigenvalues, then this was tending to a multiple of vi, and all these were vanishing very fast. Now, from that way of looking at it, it appears one has everything to gain by doing as many iterations as you like. But we're talking about exact computation at the moment. The offending things are diminishing very rapidly. All the mu, the mu i's are very large compared with the mu I, the selective ones, very large compared with the other mu j's. And so in one iteration you get a big attenuation of the things you don't want. If you do 2 iterations, you beat them down even further. And so it seems as though it would be good to do as many iterations. There'll be no harm in doing as many iterations as possible. It may not do any good because you might get as good as an answer as you could get first time, in which case more iterations would be wasted. But all our original strategies were based on the implicit assumption that we didn't want to do any more iterations than necessary, but it would never do us any harm. And then we found empirically that it wasn't true. And it was first observed in connection with the Frank matrix. And remember, I used the Frank matrix of order 12. Just in case you don't all know what a Frank matrix is, it's a matrix that's 3, 3, 2, 1, 2, 2, 1, 1, 1. That's a Frank matrix of order 5. It's up in Hessenberg. And so in general, I think you can see from that what the general form is. Now, it turns out that this is an ill-conditioned the smaller eigenvalues of this matrix are ill-conditioned. Small changes in the matrix make quite large changes in the smaller eigenvalues. The larger eigenvalues are comparatively insensitive. Now we did a Frank of order 12, which is already has some quite ill-conditioned roots, and we used inverse iteration with the roots obtained by the QR algorithm, which we knew were good in the sense that they always, we have the overlying error analysis of the QR algorithm, says all the computed eigenvalues are exact eigenvalues with some A plus E, where E is of noise level relative to A. Okay, well, our original algorithm tried to get away with just 2 iterations, and we did 1 iteration. We happened to store both vectors. We found the residual after 1 step, and it was of order 10 to the minus 12, which, since we have a 12-digit decimal computer, was really extremely satisfactory and as small as could be expected. And then we did another iteration, and the residual was 10 to the minus 4. And, well, the first thing we thought was, well, we did it wrong. There was some error in the program. And then, failing to find it, we decided that perhaps there wasn't. And we tried doing several iterations, and we found that thereafter, the residuals always seem to be around about 10 to the minus 4. And this occurred with 3 or 4 of the smallest eigenvalues. Well, then we said, well, I don't know. We didn't quite understand. It seemed rather puzzling thing, since everything seemed to indicate that another iteration there, it might not do much good, couldn't very well do much harm. And so we tried some Franks of a higher order. We did one of order 20, which is by now pretty fantastically ill-conditioned. And we found after 1 iteration, residuals of order 10 to the minus 12. After 2, 3, 4, about 10 to the minus 1. Seemed a very, very puzzling phenomenon, and being a bit peaked, it was very satisfying just to blame it onto the rounding errors. They are very good things to take the rap. You've got almost singular matrix. We thought, well, that's why it is. But when you look at this analysis, it doesn't do anything to explain it. And so we have to try and understand why this comes about, and could we, if we'd been clever enough, have predicted it was going to happen. And it turns out that we could have done. Jim Varro was the first one to give the clue to it. He did it by considering the case when this is a defective matrix, and showing that in the case of a defective matrix, yes, this is just what would happen. But it didn't really shed very much light on what exactly had gone wrong with our intuitive ideas about a non-defective matrix, which just happened to be ill-conditioned. And now I think we'll just see why that occurs. We start off with our arbitrary vector x0, which is sigma alpha I ui. We're assuming it's not defective, and so we've got a complete set of eigenvectors, and we express our arbitrary vector in terms of it. And now we see, after 1 iteration, let's assume we're taking p nearest to lambda 1. After 1 iteration, we'll have that x1 is alpha 1, and supposing p is equal to lambda 1 minus epsilon, so we're pretty close to it, we'll find that we get lambda 1 over epsilon times u1 plus sigma from 2 to the n alpha I over lambda I minus p times the ui. And p, we're assuming, is not all that close to the other ones. So this one is enriched enormously. It's blown up by this factor 1 of epsilon. These are not enriched at all. And when you normalize it roughly, you get alpha 1 u1 plus sigma from 2 to the n alpha I epsilon over lambda I minus p times ui. And these are all attenuated. Okay, another iteration, alpha 1 u1 plus sigma from 2 to the n alpha I epsilon squared lambda I minus p squared ui. These are smaller still, and therefore, well, that's where we started. We expect a second iteration to make things better. And so why doesn't it? Well, the whole trouble comes in our rather careless use of this basis ui. If we had a normal matrix, or most likely to be in practice a real symmetric matrix, we will have an orthogonal basis here. And if we take an arbitrary unit vector and expand it in terms of that basis, the sum of the squares of the alpha i's will be 1. Each individual alpha I will be less than 1. And if we take a random vector, it will be fairly balanced. But what happens in the case when you have ill-conditioned eigenvalues? Which, of course, you can only have ill-conditioned eigenvalues with non-normal matrices. It can't occur with any normal matrix. Well, you find what will happen. Just let's take the case where we have a pair of very ill-conditioned eigenvalues and all the others are well-conditioned. What will happen is that V1, U1 and U2 will be fairly close together. Look, two vectors like that. And in fact, this matrix is probably getting near defective, and of course the eigenvector is going to fall together. And the other vectors, I can't draw them in 12 space, but they're all making decent angles with each other, and they're away from these. Now, you're trying to express an arbitrary vector in terms of this rather skew sort of basis, and now you can't say too much about these alphas. So let's, for the moment, use U1, that one's all right, and U3 to UN, they're okay. But let's take as our second vector the difference between those two, which I call V2. It's the difference between U1 and U2, normalized by dividing it by the length. So this V2 is U1 minus U2. It's going to be a small vector. I've normalized it by dividing, the basis I'm going to take is U1, V2, U3 up to UN, and V2 is the normalized version of that difference. Now that second vector will now be okay, and now this will be a sensible vector, a sensible sort of basis. And if I take a unit vector and express it in terms of those, it will be alpha 1 U1 plus alpha 2 U2 plus a sigma alpha I UI from 3 to n. Sorry, V2. And I won't accept the alphas will be sensibly distributed. If I talk about statistical distributions going to random vectors, there will be nothing very exceptional about the alphas. But now let's see, in order to see what will happen when we do inverse iteration, and remember the moment I'm talking about exact inverse iteration, I have to go back to my u's because unless I've got it in terms of the u's, I can't see the effect of a one inverse iteration. And this becomes alpha 1 U1 plus alpha 2 U1 minus U2 over eta plus sigma from 3 to n. And this is now U1 into alpha 1 minus 1 over eta, minus alpha 2 over eta, plus U2 into minus alpha 2 over eta, plus sum from 3 to n. And so, if you look at these two components, what happens if you take a random vector, it's virtually certain that it will have large components of U1 and U2, which are almost equal and opposite. And together they will give a sensible ordinary size contribution to the vector itself, and the rest will just make up and be nothing significant. And the fact that a random vector is virtually certain to have this structure is the thing that does the damage. Now let's look at one step of inverse iteration. We will get, after one step of inverse iteration done exactly, we will get U1 over, now I'm going to assume that lambda 1 minus p is epsilon 1, and lambda 2 minus p is epsilon 2. Epsilon 2, in this case, is likely to be fairly small too, because although ill-conditioned eigenvalues needn't be pathologically close, they will be on the close side. So it doesn't really affect the argument very much. We'll do one step of inverse iteration, and the y, this is x naught. The y I get, which is the non-normalized thing, will be U1 over epsilon 1, alpha 1 minus alpha 2 over eta, plus U2 over epsilon 2, minus alpha 2 over eta, plus the sum of other things, and they are of order unity. There's nothing very special about that other sum. There will be large growth. And what sort of growth? Well, the size of this one is roughly dependent on eta epsilon 1. And the size of this one, of course, is 1 over epsilon eta 2. But now these two won't cancel out. And so generally the size of this vector will be roughly that. So in one stage of iteration, this is the growth you'll get. And we saw that it's the growth that determines how big the residual will be relative to the normalized vector. And so that if I did this exactly and now form the residual corresponding to the normalized version, I would have A minus pi times the normalized x1 is of order eta epsilon 1. Okay. Now we do, so let's roughly normalize this. I don't have to normalize exactly. My normalized version will be x1 equals u1. I'll multiply by epsilon eta, and I get alpha 1 eta minus alpha 2 plus u2 epsilon over epsilon 2 times minus alpha 2, that is there, isn't it? Plus all the other vectors which are of order epsilon times eta times epsilon 1. So that's roughly what a normalized vector will look like. It will now, its component of u1 will be more or less minus alpha 2. The component here will be alpha 2 multiplied by that ratio, which will probably be on the small side, but we don't care very much about that. But there's no longer any sort of cancellation. Now we do the next step of iteration. We have y2 equals u1 alpha 1 eta minus epsilon 2 over epsilon 1 plus u2 epsilon 1 over epsilon 2 minus alpha 2 over epsilon 2. And what sort of growth takes place this time? The only growth we get is a growth of order 1 over epsilon 1. And we've lost that eta, and we never recapture it again. So the second time, the residual, the first time we saw the normalized vector gives that sort of residual, the next time the residual is just a modest multiple of epsilon 1. And this is where the trouble comes. Of course, I've just described the case when all the ill condition is concentrated in 2. If you look at the Francis algorithm of order 20, you'll find the last 6 or 7 they only if you were to do the Schmidt orthogonalization process on them, they determine one vector, one direction well, a second one rather badly, and the third one scarcely at all. And so you have sort of a generalization of this analysis, and you find what I've discussed here is even more exaggerated than I've described. And so you see that the phenomenon which appears so mysterious would occur with exact computation. It's got nothing whatever to do with rounding errors. When you've got an ill-conditioned matrix, for almost any vector you start with, one iteration will give you a vector which gives you a small residual, and subsequent iterations will give you vectors which do not give a small residual. So if you look at the algorithms we have in the handbook, you will find that those associated with non-normal matrices, that is, the ones that occur in associated with HQR, are rather different in style from the inverse iteration which is associated with real symmetric tridiagonal matrices. Everything I've been talking about here, it just has no relevance whatever to the real symmetric case, because then we have an orthogonal basis. This situation I'm describing just can't arise, and there's no harm in doing a second iteration. You'll hope, if you organize it properly, and if your lambdas are very good approximations, as they will be in the real symmetric case, one iteration will suffice nearly always. But if it doesn't, a second iteration will do the trick, and if not, perhaps a third, though you have to be very, very unfortunate with your first vector ever to get to a third iteration. When you look at the thing that we have associated with a non-normal case, you find our strategy is entirely different, and we insist on getting our vector in one iteration, so it ceases, in fact, to be inverse iteration and becomes a direct method. And you might say, well, what do you do if you don't get the large growth first time, which of course could happen by misfortune if you happen to choose an initial vector which was almost entirely in this subspace. Then you wouldn't get the growth anyway, the first thing. Even this wouldn't save you and give you the big growth. And so what we do is we we do one iteration, probably 90% or even more on more percentage of the occasions, it will give the big growth. The big growth implies that when we find the residuals, they will automatically be at noise level. If we don't get the big growth, then we take a different right-hand side. We take a different initial x0, and in fact we're prepared to run through a whole orthogonal sequence of x0s, of initial guesses, until one of them gives the full growth on one occasion, in one iteration. Now this might sound a rather unsatisfactory process, but I pointed out a random vector will usually contain a reasonable component of alpha 1, and so on nearly all occasions one iteration suffices. Just occasionally it takes two, and you can, if you have a good deal of malice, invent one that takes rather more. But the error analysis shows that there will always be one which gives the full growth in one step, provided only your lambda is exact for some a plus e, where e is of noise level, and that is guaranteed by the overall error analysis. Well, yes, perhaps there's only one other thing that needs to be said here, and that is one of the unpleasant. I think that the mathematics behind it is very interesting. This last thing I find absolutely fascinating. The fact that you could really explain this mysterious behavior pleased me a great deal. Is very, very, very efficient. The inverse iteration is always done either with a tridiagonal matrix or with a Hessenberg matrix, so that the whole process of doing one step of inverse iteration is very fast. The main snag is that if you consider the real symmetric case, you want to get eigenvalues which are, you'd usually like to have eigenvalues which are almost, which are orthogonal to working accuracy. For many purposes, the user really does have this requirement. Now, let's start off, first of all, with two vectors which are rather close together, lambda 1 and lambda 2, rather close. Now, and we're dealing with the real symmetric case. Even in the real symmetric case, all we can guarantee is the x1 and x2 we get, that x1 will be an exact eigenvalue of some a plus e1, and x2 will be some eigenvector of a plus e2, where e1 and e2 are both at noise level but different matrices. And unfortunately, that means in the case when lambda 1 and lambda 2 are close together, and eigenvectors of this matrix are then very sensitive to small changes, although we will get two eigenvectors, there's nothing to insist that they will be at right angles, because one is an eigenvector of that, and one is an eigenvector of that. Although they're both close to A, eigenvectors are very sensitive. And so you will not get this orthogonality between them. Judged individually on its own right, they will be just as good as those got with a routine like the Jacobi process, which automatically gets orthogonal vectors. In fact, those given by inverse iteration are usually rather better than those given by any other process we have. But this lack of orthogonality is a weakness, and therefore you find that in the program tristem, which gets vectors of a symmetric tridiagonal matrix, we orthogonalize them after we've got them. And there are lots of tricks, little tricks used in it to make certain that this orthogonalization relation is obtained, and we do get a full set of vectors spanning invariant subspaces belonging either to eigenvalues which are equal to working accuracy or rather poorly separated. Now, when you come on to the non-normal case, you can't really work like this. After all, the eigenvalues are not, the eigenvectors are not orthogonal, and you have to distinguish between the cases where, say, the eigenvalues really agree to only to half the figures. It's a comparatively well-conditioned eigenvalue problem. You then get your two eigenvectors, which might make an angle of, say, 30 or 40 degrees. If you were to orthogonalize those, you wouldn't really be getting anything like the eigenvector corresponding to the second one. The two together, though, would span the invariant subspace. And so you have a rather difficult situation. I'd like to say more about this when discussing shortcomings of the algorithms in the handbook. I'd like to stress at this time these shortcomings are something which are inherent in the problem. They are things that a customer may feel dissatisfied about, but they are not what I would call real weaknesses of the program. It's just a matter of deciding what you would really want the program to give, whether there's anything different from what we've given, which you would prefer. But I think if you fully understand what the possibilities are, you will probably agree that they are not weaknesses in the program, just difficult decisions that have to be made. Right, I think that's probably all I say about inverse iteration.